Welcome to another ISO Backgrounders. In this session, we're going to talk about TCP/IP, which is the pivotal addressing method which has been used since the dawning of the internet. In our ISO model, it pretty much defines the network layer. As the network has grown, so has the complexity of the addressing methods. We'll talk about how, over time, we have evolved into a system that lets us send and receive messages to the billions of devices that are now all interconnected. In this session, we'll talk about the makeup of the IP address and how some significant adjustments have been made to it over the years. We'll talk about routers, the directory name server, IPv4, MAC addressing, and packet routing. Along the way, I'll touch upon some of the special use addresses and how the IP address can be used for geolocating. And along the way, I'll throw in IP masking, subnetting, ports, and firewalls. So let's get. At this point in our computerized evolution, the dominant machine architecture was 8 bits, and in turn, moving data or organizing data was in 8-bit words or octants. Addressing had evolved into the use of 4 octants, which gives us a value of 256 4 times, and we separated them by these dots. Now, by 1981, an international group got together and tried to establish worldwide IP standards. They had recognized that probably our adventure with radio had demonstrated the problem that if every country sort of does its own thing, takes better part of a decade or two to unwrangle it, and they wanted to speed this process up. And so they tried to establish worldwide standards. Now, the first thing they realized is there'd be a bunch of large networks that countries needed and militaries needed and that kind of thing. And so they allocated a bunch of these addresses, about half of them, from 0 to 126, to be these large standards. And that allows for 16 million plus addresses that could be allocated to these very large networks. They envisioned a mid-sized situation, which were corporations and those sorts of things, banks and telephone companies, that kind of thing. And they then went ahead and said, okay, we'll use an additional bank and only allow for 3 octants, which ended up dividing it up into 16,000 some odd networks, each with 65,000 addresses. And then the rest of them were allocated to smaller situations, which was 2 million addresses or 2 million networks, each with 256 addresses. Now, do you see anything wrong there? I mean, we're looking here from our perspective, but at 16 million addresses, how many Class A's do the United States need? And we're talking just one address, and there's 342 million of us. If you only had one address, what would you do with it? In addition, could a company like Verizon or an airline or anybody exist on Class B? That's 65,000 total addresses. It just didn't have the vision. It didn't cover things. But at the time, there were only 30,000 computers worldwide, and it seemed like more than enough. But by 1996, we had to do some major surgery, and it was already up in place and running, so we could only just add things to the details. First, they divided the concept of public versus private networks, and that most machines would be controlled and administered on private networks, which they could take off the table. But public addresses, again, at this point, they realized they needed lots more, and they sort of reallocated them in a way that they help you with geopositioning and that kind of thing. But the idea now is that we would reserve certain address blocks that are for internal networking, and each of the classes had their own internal designation, and they could use them for what they want, but they couldn't leave the local network. When you went out into the public sphere, you put on a public address and you sent it out, and you returned it, and you returned it back, and then converted it back to your private addressing scheme. And that's what Nate is about, which we'll talk about in a few minutes. That still obviously comes up far short. And by 1998, we had a revision, IPv6, which allocated 8 sextants. These are now 16-bit words, and there's 8 of them. That extends the length of the address from 32 bits to 128 bits. And, again, this was all up and running. They could only add this as a secondary thing to the original packet, and it had to keep the network up and running. And so there's an IPv4 and an IPv6 in the header record now. But that allows us to put multiple devices on the same IP address, and in turn expands greatly the capacity of what we could do. Let's talk for a minute about the packet. The packet is about 1 kilobyte in size, and there's a header record on it, and that header record has the to and from address and various other metadata elements, like sort of where it went, how it got there, how big it is, what order it was sent. And a given machine, here's our internal network 0, machine 5, might drop a packet on the network and send it on its way. After that, we attach the body, and there's really no real reason anybody would need to look at the body, but at this point, most times it's encrypted because of security reasons, and we don't actually have to see what's in there. But because we're focused on what the header record's doing for us. Then it off to a router. Now the router has the job of just saying, okay, I see this packet, I need to send it on its way. So I send it down this wire or that wire, and does other things, but that's its basic function. It does optimize for which way is the fastest, given that network lags and whatever. It's polling, keeping track of which direction seems to be clogged, and tries to send it different ways. On the receiving side, we have the network card, and at the time, machines were very slow, and the first thing to do was to strip off the chaff to get to the wheat. You only dealt with things addressed to you, and you ignored everything else. So there's a little switch there that says, is this for me or not? And I take it in. Now, packet's going to arrive in the wrong order. And so there needs to be buffering there, and reconstruct the packet so that the movie or whatever is reconstructed and plays back to you in the right order. Now, the internet was evolving rapidly, and local administrators were doing all kinds of other things to make things, usable for them. There's a concept of ports, which is the concept of channels that again, the times when machines were slow, or you really wanted to de-escalate the sort of error message handling you wanted to do, you would target a certain service or protocol to a given port, and um, you can then deal with it more simply. Another concept here are firewalls. If you don't want everybody to just get into your stuff or see your stuff, you want to be able to limit people's visibility to what you're doing, and so you only open up certain ports and you only allow certain protocols to be responded to on those certain ports. That's an internal control you have, and it gives you the ability to hide your stuff from hackers and and again organize things in ways that it's easier for you to you know comprehend and deal with the sort of information you're going to receive. They ended up assigning 4 digits for that, which gives us 10,000 options. Um, Another thing that evolved is that the MAC address, the idea that we actually want a machine to be defined and stay a machine regardless of where it goes or what addresses get assigned to it. So we need this other reference point. We need the ability to say, yeah, this is an actual machine. And that's done by actually burning an IP or a MAC address into each device. And those are, randomly created in a way that every machine has a unique ID. And that's burned in the machine. Talk about Nate for a second. Uh, there's actual process where if you are taking your local address and putting it out on the network on a public address, if you get that packet back, you need to then say, this was my local machine such and such, and so you need a conversion table from internal and external addressing, and that's what the Nate table's about. I thought it'd also be interesting to talk about the sort of addressing that you see every day, probably on your browser, right there in the box. Um, Deconstruct it here for you for a sec. Uh, that first section is a designation of the protocol or service or what have you that you are wanting to speak, wanting to talk to. Um, it can be any number of things. It can be a mail server, it can be a database, it can be a file transfer. The HTTP stands for hypertext, and that's the protocol that browsers are designed to respond to. And in turn, that's the one you see in your browser. It's all filtered at this point. Now, if the S is there, that's a secured socket, which means that the packet was encrypted, and there's methods to ensure that the encryption wasn't violated. And so if you see the S, or if you're conducting a financial transaction and you want to make sure it's secure, make sure the S is there. The browsers usually also show a lock or keys indicating that the secured sockets are intact. The www was a designation of the World Wide Web, and it has its routing things as well, but it's not required to be there, and it can be used for other things. And more often than not, the internal administrator is using it as a router vehicle, and it's defining which machine I'm going to send it to once I get it. And in turn, if you bring up a more complex website, or you need to, branch to forums or whatever, this is sort of the way you go about that. Then, of course, the actual domain name, which is just meant to be a user-friendly English, easy to type name, so you don't have to deal in all of these complex IP addresses. You can just say, I want to speak to Google, and it knows where to take you. After the dot, there was originally half a dozen of them, com or gov military. That was originally used as a major branching point because, again, machines were slow, and and also the military was real insistent that they wanted to handle their own security, and everybody stay away from their stuff. So they stripped off anything with a .mil, and it goes its own way. And the international standard was there were country codes there, and there still are, but it has evolved into anybody who wants to put up one of these name server type of things to convert IP addresses to something more easy to deal with. You can now pretty much have anything after the dot. Then, of course, the ports we talked about earlier. There's 8 digits here, and we need to, or there's 4 digits here, and it represents 10,000 different channels. You can manipulate, hide things, so on and so forth. The standard also allows for subfolder, which is readily used to say, I want you to, go to this set of pages or these form handling systems or whatever. It gives you the ability to route all kinds of detail into the address. And then you'll see the question mark. And after the question mark, anything goes. It's all yours. You can construct it as at will. Generally, these are pass parameters. They're not encrypted. You use them as quick and dirty things, but it makes for a convenient tool in your arsenal. So I've covered a lot here and violated the idea that we are in the transport layer. But if you're talking about physical things like routers and ports and MAC addresses and whatever, those are really topics for the network layer and the data link layer and the physical layer. And if you're talking about user-friendly names and the sort of protocols that you're used to seeing, you're talking about the session layers, and the application layers, which are above you. But reality is, without the transport layer, there's no internet, and that's what we're talking about.